Have you ever stopped to think about the map on your phone? Or how you can stream a live event from the other side of the world? It all depends on this invisible network, orbiting hundreds, even thousands of kilometers above our heads. Today, we're going to pull back the curtain on the hidden backbone of our modern world, satellites.
I mean, really think about it for a second. That little blue dot on your screen that's guiding you through traffic, that's a satellite talking to your phone. That live game from halfway across the planet? Yep, satellites again. And being able to get internet in the middle of nowhere? All of these things we kind of take for granted are only possible because of this incredible infrastructure way up in orbit.
But how does it actually work? We get what they do for us, right? But this time we're diving into the how. How do these super complex machines stay up there, and how do they talk to us all the way down here on the ground? Well, let's get into it.
To really get a handle on this, we've got to start with the fundamentals. What are we even talking about when we say the word satellite? This is our unseen infrastructure.
You know, from an engineering perspective, it's actually pretty straightforward. A satellite is just an artificial object that we've launched into a very specific path, an orbit around the Earth. Its whole reason for being is to do a job for us, whether that's bouncing signals around, figuring out where we are, or snapping photos of our planet.
Basically, every satellite is like its own self-sufficient, high-tech robot with four main parts. First, you've got the payload. That's the whole point of the mission, like the cameras or sensors. Then you have the transponders and antennas, which are kind of like its ears and mouth for handling all the communication signals. And finally, the power system, those solar panels and batteries, that's the heart of the operation, keeping the whole thing alive.
So we've got this high-tech robot zipping around in the vacuum of space. How in the world do we actually talk to it? Let's follow the signal.
It's really like a giant, cosmic game of catch. A station on the ground shoots a radio signal up to the satellite. We call that the uplink. The satellite catches it, boosts the signal, cleans it up, and then throws it back down to a receiver somewhere else on Earth. And that's the downlink. Uplink, downlink. That is the fundamental rhythm of all satellite communication.
All right, now this is where it gets really interesting. Where a satellite lives in space is just as important as what it does. These orbits are like superhighways in the sky, and picking the right one is a huge engineering decision.
Yeah, the altitude of an orbit completely changes what a satellite is good at. So just how different are we talking here? The scale of it all might just blow your mind. Let's start kind of close to home. Low Earth orbit, or LEO, starts at a pretty nearby altitude of about 160 kilometers. To put that in perspective, that's roughly the driving distance from, say, New York City to Philadelphia, except you're going straight up.
Okay, now compare that to this. Geostationary orbit, or GEO, is at an absolutely immense altitude of nearly 36,000 kilometers. We're talking almost 3 times the diameter of the Earth itself. The difference in scale is it's staggering.
And this table here really lays out the critical trade-offs. Over on the left, you've got LEO. It's so close that signals travel fast, giving you really low latency. That's perfect for responsive internet. Way over on the right, GEO is so high up that a single satellite can see a huge chunk of the Earth, and it stays locked over one spot, which is exactly what you want for continuous TV broadcasting. And MEO, medium Earth orbit, that's the Goldilocks zone, right in the middle, a perfect balance for systems like GPS.
So with these different orbital superhighways, engineers can match the road to the specific job. Let's take a look at how the mission really dictates the design. So this is the key. Engineers aren't just picking these orbits out of a hat. The choice is completely intentional, and it's all based on what that satellite's main goal is.
It really all boils down to the goal. You want fast, snappy internet like Starlink? You need LEO. The signal path is super short, so that delay, that latency is tiny. The trade-off? Well, you need a whole fleet of them, a constellation, to get continuous coverage. But for TV broadcasting, you want GEO. One satellite parks itself over a continent and provides an uninterrupted signal. The trade-off there? The signal has to travel so much farther that it creates a noticeable half-second delay.
So what about MEO, that middle ground? Well, it turns out it's the absolute sweet spot for navigation. A constellation of satellites in MEO, like our GPS system, gives you continuous global coverage. But you don't need the thousands of satellites that a LEO system would, and you don't get the huge signal delay you'd get from GEO. It's just a really elegant, balanced solution. Of course, sending these signals across thousands of kilometers of space isn't exactly easy. It comes with some really serious engineering hurdles, and it also points to some super exciting things happening in the future.
You know, engineers are constantly fighting against physics.
Signals just naturally get weaker over long distances, that's path loss. The speed of light, as fast as it is still a hard limit, and that's what creates signal delay. The radio frequencies are getting crowded, so you have to be really careful about interference. And don't forget, these satellites are totally on their own up there. They have to generate and store every single watt of power they use, all from the sun.
And that brings us to the biggest trend in the industry right now, launching these absolutely massive constellations in low Earth orbit. We're talking thousands of satellites all working together to blanket the entire planet in high-speed internet. It's a total paradigm shift.
And that really gets to the heart of it all. At the end of the day, that's what this is all about. Satellites are our way of breaking free from the limits of ground-based networks. They're what enable true global connectivity.
So what are the big takeaways here? Well, first, a satellite's orbit is a very deliberate design choice. It's not random. LEOs for speed, GEOs for coverage. And maybe most importantly, these things are a critical part of our global infrastructure, connecting the unconnected and making so much of modern life possible.
Which leaves us with a pretty fascinating question to ponder. As these new mega constellations with thousands of satellites come online, our sky is literally changing. How is this more crowded, more connected space going to alter our relationship with the planet and with the stars themselves? It's something to think about. Thanks for watching.